So this is kind of a hodgepodge video that's going to cover three primary topics. The first topic is now actually kind of hidden because I didn't want to give too much of it away. But it's going to be looking at specifics of elimination reactions and then the potential for the formation of a nucleophile. And then we'll look at some acid-base kind of leveling effect decisions when looking at mechanisms. And then we will look at the dreaded intramolecular reactions. Okay, so to go ahead and start, if we go through and look at this, what information do we have that would allow us to decide where we're going with it? Okay, so hopefully what we would do is recognize that we have very good leaving groups with the bromines, and what might make this one a little bit more interesting or potentially troublesome for us is that we see that there's two of them. Before we freak out too much at our substrate, it might be nice to take a look at what we have floating over the reaction arrow, and we do notice that we have an NH2 bonded to an Na. Okay, which I know I just completely made that impossible to read, but that Na is a big old hint that what we're looking at there is NH2 with two lone pairs and a giant negative charge. Okay, so deciding where to go. Negative charge. As soon as we see a negative, we might be immediately thinking nucleophile, particularly because we've been doing lots of substitution reactions, but remember, we've also been doing elimination reactions, and negative charges are just as likely to be found on bases. Okay, so what should we predict with this? Okay, well, bit of hidden information that isn't explicitly stated either, I think, in the textbook or in the slides until this moment, is that nitrogen is actually a pretty crap nucleophile. Okay, and the reason being is, let's see what would happen if it acted as a nucleophile. We would then generate our NH2, okay, with a lone pair of electrons on it. What could that lone pair of electrons do? Well, it could react again. Okay? So nitrogen is not so much that it's a bad nucleophile, it's that it's a nucleophile that is virtually uncontrollable, which means it just does whatever the hell it wants. So if we are going to see nitrogen show up in a reaction, it's probably not going to act as a nucleophile because it is an uncontrollable nucleophile. Okay? And that's a bit of an overstatement, but it's not too bad. Okay? And being uncontrollable means that if we're going to see it, it's probably not acting as a nucleophile, which means we're probably looking at it act as a base, which means in this case, for this particular reaction, we're probably going to run this as an elimination. Okay, so now a fun question. Where are we going to do our elimination? Okay, well, we've got lots of different hydrogens that we could potentially remove. Okay, we've got a hydrogen in here that would be beta to what I will call our red bromine. We've got a hydrogen in here, which would be beta to our purple bromine. And we also have hydrogens located in here, which would be beta to our red hydrogen. Okay, so if we're doing this elimination, we might push for the most stable elimination product. And in that result, we might go through and say that we want to remove the black hydrogen. Right? And so that we get that elimination product. Right? It's not that that is necessarily a bad choice, but let's take a closer look at that blue hydrogen. Okay? That blue hydrogen, and for that matter, the green hydrogen, are probably both more acidic than the black hydrogen. Why? They are closer to an electronegative element, which would suggest those are going to be the better ones to remove. Okay? We can theoretically remove any of these and they will all end at the same path, but that path is confusing and convoluted. So if we're seeing this double leaving group side by side, let's focus on just removing the hydrogens at those carbons. Okay? Which means, whoops, pretend you didn't see the man behind the picture. which means let's go ahead and just remove the blue hydrogen because it's going to be the most accessible and easiest to eliminate, which means we would end with this structure. Okay? We now run into a bit of an issue. If we try to remove that green hydrogen, we'd be removing it from an sp2 carbon, okay, which sp2 carbons are slightly more electronegative. Why not? Okay, couldn't it be removed? The problem again has to do with kind of the stability of that. If we remove that hydrogen, we'd be forming a negative charge on our carbon structure, which is not particularly stable. Okay, and where you might go with that is then, well, couldn't I have said, instead of removing the hydrogen, say remove the bromine first? Because then I would have something that could stabilize that negative. Okay, and I like that logic, except what did we say in the last video about the hybridization on that carbon? Well, that was an sp2, and we said we should not be having that do any kind of chemistries. So this reaction is not an easy step to undergo, okay? But there is the potential for it to happen, okay? What do we need for that to happen? We would need, and actually let's show it as the sum of the piece or the parts. We said remove the hydrogen first. I guess I should actually show those arrows. I didn't show any of those curved arrows. Yeah, what kind of instructor am I? Clearly not a good one. Green, remove it to the carbon. Okay, have the bromine leave. And so if we show it as the individual parts, we can then represent that as the resonance structure. Okay. One of the things that becomes tricky here with this is making sure we don't lose carbons. That black carbon is sp hybridized, which means the bond angles need to be 180, so it is very easy to lose carbons through this reaction, so be aware of that. And I have totally, for the record, completely lost track of where I was going. Well, crap. So it's not an easy reaction to run. So doing that second elimination is not favored. So what things might we need to do to help that along? Well, we'd want to use an incredibly strong base. Well, we're not using hydroxide. I thought hydroxide was our strongest base. Okay, well, let's evaluate that. Which is the stronger base? NH2 minus or hydroxide? Okay, well, they're both the same charge. If we look at size, they're in the same row, so they're the same size. What about electronegativity? Well, oxygen is more electronegative, so that must mean it's a stronger negative. If it's more electronegative, what is it doing with its electrons? Increased electronegativity means it is holding its electrons. Why is that relevant? Well, what does a base need to do? A base needs to donate its electrons. Because oxygen is more electronegative than nitrogen, that means the oxygen is actually less basic than the nitrogen. So to run this reaction, we're actually upping the strength of the base significantly so that we can get this reaction to run. Okay? So we can effectively force it to go by throwing a stupidly strong base at it, and that's what's happening here. Okay? So, as a summary, if we pull all of that information now away, clean that up a little bit, what we end up forming is that triple bond, also known as an alkyne. Ta-da! And we formed that through an elimination reaction. Okay, before we take this too much further and reveal more information, actually no, we'll reveal a little bit more information down here. We're looking at a starting material with two leaving groups. Those two leaving groups can be on neighboring carbons. They could also be on the exact same carbon. And we end up getting the same end result. Okay? Depending on the exact details of the of our conditions, we actually usually will end with an external or a terminal triple bond. Okay, and the reason for that is actually has to do with this, what the heck is that A for, and this empty white space out here. Okay, well, let's take a look at our alkyne. Have we shown everything on it? No, there's an implied hydrogen there, right, that we would see in our IR showing up about 2200. Okay, why is that important? Well, what did we say the hybridization was of those carbons? Well, those carbons are sp hybridized. And if they're sp hybridized, they have an increase in electronegativity. So much so that they actually become more acidic. Okay? So here becomes an issue. We now have a red hydrogen on there, and we just addressed that these are now more acidic. Well, how much more acidic are they? Well, that's going to have to do with their pKa's. And if we look up the pKa, damn it. So pause. Sometimes you got to love pause. You would need to look up the pKa way back when on slide 15, which was something like 20 videos ago, more like 10. And the pKa of the alkyne is about 25. The pKa of an amine is about 35. Well, if we go through and look at this, we can't directly use the pKa's as written because the pKa is only going to refer to the acid form. The alkyne is in its acid form. The amine is not in its acid form, so let's go through and run our acid-base reaction. Go, oh my God, a negative carbon. There's no way on this green earth would that ever be allowed. Now that I have the acid form of the amine, I can write in its pKa at 35. And if I were to predict the equilibrium, which way that reaction arrow should go, it would definitively go to the larger P. That's going to the right, isn't it? Yeah, that's going to actually say that in this case, we do another acid-base reaction and we form that stupidly negative carbon that we thought was not reasonable to form. Yep, it is. Okay. That acid-base reaction is one of the big drivers for this reaction actually occurring. Okay, because forming those pi bonds, those are endothermic reactions. That's going higher and higher and higher in energy. Because we follow those exceptionally endothermic reactions up with a highly exothermic acid-base reaction to form this stupidly negative carbon, that's why this reaction works. Okay? But what if I wanted to end with the alkyne? Okay, back here. Well, now what do I have to do? Okay, well, I would have to do a second step. Okay, so after this thing has happened, because really it doesn't end at that blue structure, it ends as the black structure, I would have to do a second step where now I add a little bit of acid. Okay, that acid would go ahead and protonate the alkyne, and I'd now be back where I wanted. Okay, so this is a notoriously challenging reaction for students to go through and do because it is typically written as step 1, sodium amide, followed by step 2, H3O+. That 1 and the 2 written over our chemical reaction arrow are referencing reagent steps, not mechanistic steps, but reagent steps. And one of the things that becomes challenging, particularly with this one, is you go, well, why do you have to add H3O+? If we just add the sodium amide, it goes to the alkyne. Yes, but then it continues to go to that black alkyne, the anion form of it. If I add just sodium amide to this dihalide, it doesn't stop at the alkyne. It goes all the way to that negatively charged species. To get it at the neutral alkyne, we will almost always have to follow up with an acid to put the hydrogen back on. And you'll note, for those of you really listening, I said almost always. Why almost always? Because almost always we remember that we need to do this as 2 steps, both as students and as chemistry instructors. So oftentimes chemistry instructors will forget to add that second step. Then you don't have to do it. So if your chemistry instructor F's up, then you don't have to do the extra step. If they're paying attention and they're doing it right, then you have to do that second step. That kind of sucks, but that's the way it is. Okay. Why does this become important for us though? So let's just say we only did step 1. We would then end with that negatively charged species. And what is special about a negatively charged species? That negatively charged species can now act as a nucleophile. Why does this become incredibly cool and important? I have a nucleophilic carbon. Okay? Carbon that has an exceptionally low electronegativity that by all rights should not be able to stabilize a negative charge. I now have one. That negatively charged carbon can now go through and I can make larger carbon structures with this molecule. Okay? And that's going to be such an important layer of chemistry for us. Okay? And so rare, in fact, that in second semester, when we talk about negative carbons, it is so rare that we don't reference them as negative carbons. We call them Grignard reagents. We call them Wittig reagents. They get names. They get the names of the people that discovered them because negative carbons are that rare to find. Okay? So this is a really big deal that we have this negative carbon. It allows us to actually build larger structures, and that's pretty phenomenally cool. How do we build them? Well, with a nucleophile, I need to react that with an electrophile, and I could react that in what is known as a substitution reaction. And in fact, I could stepwise that up a little bit more. Instead of just SN, I could call it SN2. Why 2? Because that is a negative charge, and that's going to be a strong nucleophile, and strong nucleophiles run under SN2 mechanisms. Whew. That was a lot. Okay, so let's clear that all away and reveal all the total secrets within this. Okay, so we end up getting 2 eliminations because we have those 2 leaving groups. Those 2 eliminations will form 2 pi bonds. Okay, the first elimination forms one of our pi bonds. The second elimination forms the second one, and we get our triple bond. Okay, so 2 sigma and a pi. So our alkene's acidic? Not really. So it's not easy to remove that hydrogen. The alkynes, much more so. So this is a very slow reaction. It takes some heat, and it takes a significantly strong base to force it along. This reference to vicinal and geminal, I always botch. One of these is vicinal, and by one of these, up here, one of these is vicinal, and one of them is geminal. It's not a big deal. But if you hear those references or hear those terms, that's what they're referencing. A carbon where you have 2 halogens connected, or side-by-side carbons with, and not necessarily halogens, but leaving groups. You're looking at vicinal or geminal. It's just a naming thing. Don't stress about it. Okay, so that was cool. 20 minutes on that cool single slide. Only 5 more slides like this to go. Kind of a joke. Acid-base mechanism extras. So we talked about that leveling effect way back in our acid chapter and said we need to make sure that when we run our reactions, we don't form incredibly strong acids or bases depending on our environment. So if we looked at these reagents, you might go through and say, just focus on the top one for the moment, that we're doing a substitution reaction, and you would be correct. We go through, we've got our O methyl out there. I see an O. Come on. Jiminy. Work with me. Okay, I see our O there. So it probably makes sense for the oxygen to attack our carbon and the iodine to come off. Okay. First thing, this is neat because where is our substrate? Our substrate is being shown over the reaction arrow. The substrate can show up wherever the hell it feels like as long as it's a reactant. Okay? So if we went through and did that mechanism, what do we get? Might as well draw it in the box. We would draw this out. We still have the benzene ring, so we got to keep that there. We can't just forget it. We'd have the oxygen connected to that carbon with the 3 hydrogens still connected to it. The iodine left the structure. Okay, the hydrogen I didn't do anything with the hydrogen, so the hydrogen's still there, and then that would be a positively charged oxygen, yeah? Okay, now what happens? Well, now our base can come in, remove the hydrogen, and we go through to form our product. And there we go, right? Everything seems copacetic. We've got octets correct. Everything looks legitimate. So what's the big issue? Okay, it's not so much that it's a big issue, but we need to make sure that our mechanism is reasonable. Okay, and this mechanism is not reasonable. Okay, why? If we take a look at our intermediate here, what we have effectively formed is H3O+. H3O+ has a pKa about -1.5. So it is exceptionally acidic. KOH is a strong base. This mechanism that we have gone through and shown is a bad mechanism because we have formed a strong acid in our intermediate in a strongly basic environment. So this mechanism doesn't accurately show what is happening with the chemistry. Kind of makes sense? So, Carty uses the leveling effect to explain this. The way that I would go through and reference it is a little bit different. Okay, and for those of you being like, I didn't copy that down, remember it's wrong, so it's okay. The way that I would go through and describe this is slightly different. Okay, and what is that slight difference? When you look at your reactants, what you should do first is not just be, oh, I want to do substitution, so let me just start substituting. Okay, what you should be doing is thinking about where there is chemistry within that box. Okay, and what do I mean by chemistry? We could look at differences in charges. Okay, we could say that that oxygen was partially negative, the hydrogen was partially positive, the carbon was partially positive, the iodine was partially negative. Those were all things that we actually took advantage of in that last mechanism. The last thing that we didn't fully address was that KOH sitting underneath the arrow. So what we did was ignored its importance. How important is it? Well, the potassium is formally positive and the oxygen is formally negative. If I'm going to run this reaction, I want to react the most reactive thing first. Okay, so in this case, the oxygen on my alcohol is not the most negative thing. That's partially negative. I want to react the KOH. Okay, because potassium is a group 1 metal, it's a spectator ion, I can effectively ignore it, and I want that hydroxide to come in and do some chemistry first. Okay, herein lies the rub on what could happen here. This hydroxide could just as easily have attacked here and caused that leaving group to leave. Why do I know that I should not be showing that? Well, look at the product. Does the product show that? No? Okay, well then don't do it. Instead, have that negative attack our hydrogen. Okay, the electrons now shuttle to our oxygen. The resulting structure is a negatively charged oxygen. That negatively charged oxygen can now react with my my methyl iodine. And those electrons can do the backside attack and kick that out. Why am I doing backside attack and running this last step as an SN2 and not an SN1? My nucleophile is strong. What did I do in the first step? The first step was an acid-base reaction. Okay? So what we want to be considering is the activity of our reagents as we go through and draw a mechanism. So with that, I'm going to go ahead and actually, no, I'll leave all that up there so you can use that to help kind of guide you through this next one. So I'm going to recommend you hit pause because I'm not going to walk through the next one. I'm just going to show an answer. So go through, try and draw out your mechanism according to what you think should be going on in this next one, and we'll come back and look at the answer. So pause, space, click, do it. Nothing like going through and solving a question and realizing you did not provide anywhere near enough boxes to go through and solve this one. So, first off, the big thing that you need to note here is that you're under a strongly acidic environment because H2SO4 is a strong acid. So in that very first step, we would expect that acid to be reacted. Strict leveling effect here written in that big black lettering there. The methanol as the solvent is probably going to be deprotonated or be protonated by the strong acid to create our acidifying species. Once we have that, then technically our nucleophile can, or our base can react with it, and we run our standard mechanism. I have no objections if you were in a mechanism to show that green arrow happening instead of the purple set there. Okay, I don't have any problems with that. Okay, what I might do is give you the purple set and say, why is this predicted to happen instead of the green one? That could actually be a fun exam question, so we'll consider that. But then we're continuing on. We've now protonated our leaving group. Once the leaving group is protonated, we have a carbocation, and you might be saying primary carbocations. I'm not allowed to form that, but that is not just a primary carbocation. That is a benzylic primary carbocation, which means it is stable enough to form. Might help if I spelled benzylic correctly. Okay, then our methanol can come in and attack to permanently stabilize that carbocation. That gives us a positively charged oxygen. Another equivalent of our methanol comes in and picks up the hydrogen, and we end with our final product. Okay, so in this, you see lots of methanols popping up in and out of this, and lots of protonations and deprotonations. And you might wonder, well, the reaction just said one of each. This isn't Gen Chem, unfortunately. The reaction does not say one of each. The reactant says at least one of each is necessary to cause this reaction to occur. Okay, so you may need to add, particularly solvent molecules, multiple solvent molecules into a reaction. How do you know it was the solvent? Methanol experience. Methanol is a very common solvent. That's how you would kind of know that. If your mechanism came up a little bit short on this, that's okay. Go ahead and take a picture of it and post it into our shared files, and I'll take a look and tell you what I think, that maybe that was good enough and you would have received credit, or maybe not. But really your mechanism should have shown all of this detail, which was kind of misleading with the one single box that I gave you. Okay. So yeah. We're going to go ahead and move that, and we'll move on to our last interesting topic. What we've been looking at is intermolecular reactions. So the nucleophiles and the electrophiles have been separate molecules. So if we think about our substitution reactions, we had an electrophile, and then we had, a nucleophile, and the nucleophile reacted, and we got our product, okay, En. In the eliminations, we had our leaving group connected, but then we also had to remove that hydrogen. So we had a base come in, remove that hydrogen to form that pi bond. So again, two species. So we're looking at intermolecular reactions. There's two different molecules happening. We do have the ability to do intramolecular reactions. Okay, and that becomes a little bit more challenging. Okay, why does it become challenging? Well, to do the intermolecular reaction, we needed a nucleophile and an electrophile, or in the elimination, an acid and a base. So those are very different chemistries. To do intramolecular, that chemistry must be found in the same molecule. Okay, that makes it a little bit trickier to deal with, because if it's in the same molecule, shouldn't it react with itself? Well, that's why it's intramolecular. But depending on the reactivity of those individual species, sometimes they can get far enough away from each other that it's not a big deal. Okay, so we could go through and look at some potential examples here. So we're running an SN2 reaction, a slightly more advanced one that we'll probably see In fact, not probably, we will see towards the end of the semester. And we form this active intermediate. This active intermediate has two chemistries. We've got this negative charge, which could act as a nucleophile or a base, and we also have this positive charge over here, which is making both the carbon and a hydrogen next to it active. We've got that electrophilic characteristic or the acidic characteristic. So if we're looking at how we transition to our product in this case, what we might notice is that we aren't concerned about the nucleophile electrophile characteristics. Our primary focus here is going to be on that acid-base chemistry. So a short-cutting, pioneering student might go through and say, well, I'm going to take that hydrogen off there and I'm going to give it to the nitrogen, or the electrons to the nitrogen, so that way I can draw less. Whereas another student might be like, well, that sounds intramolecular, that sounds a bit sketchy, I don't know that I should do that. And so what they might do instead would be to be like, okay, well, if I can't do that because intramolecular sounds bad, I was told not to do that, I could go through and find a hydrogen from somewhere. Okay, so we'll call it HA. The electrons react. We go through, we would make, okay, whoops, we got to get rid of one of those lone pairs, put our hydrogen on, and then continue out the rest of the structure, NH2 with the H, and still have the positive, and then we could have that A minus, because now it's an A minus, because right, those electrons went that way. The A minus takes those electrons and goes there, and then I would have the product. Okay, so we're really looking at this happening as doing it as one step or two steps, okay, and deciding how to do that. Well, let's deal with that first, and then we'll open up the next question. In this case, the odds that oxygen is able to get over there to react with that hydrogen are pretty limited. Okay, it's not very likely to run an intramolecular reaction there. There is a possibility of it, but it's not guaranteed. 1, 2, 3, 4, 5. So to do that reaction, I'd be forming a 5-membered ring intermediate, or a pseudo 5-membered ring intermediate, to make that final connection, okay, or to do that reaction. And that's just not super likely. The molecule probably can't flip back on itself to be able to pull that off to any real extent, which then means the solvent interactions make more sense, and that long pathway is the one we should actually show. That means you have to draw more. But you're drawing more to be correct, and don't you want to be correct? So yeah, we can't do the nice shortcut. We've got to go the long route. Okay, so then someone might say, well, but I can still shorten it. Instead of making that a second step, why not throw another A minus over here, and we do it this way, and now it's still just one step. Okay, right? I like that argument as well too. That's kind of a cool one, so we don't have to do as much work. But of course there's a problem, okay? And let's see if I can highlight what that problem might be. For that reaction to happen as drawn, you have 3 molecules all reacting simultaneously because they're all shown in the same step, which then means you have a termolecular reaction. And how frequently do we see threesomes successfully lead to long-term relationships? Yeah, that's why that one's a bad idea too. Okay, so ultimately what that means is you have to draw those 2 acid-base steps as individual steps. Okay, and that does kind of suck, but that's the way you got to do it. Okay. So how about this guy? Well, clearly in this case, we have to be doing an intramolecular reaction. Okay, in the very first step, our base comes in, removes the hydrogen. We'd get the negative charge on that oxygen. That negatively charged oxygen has to go in and do this, which means it has to be intramolecular. Well, but intramoleculars aren't likely to happen, and that's a 3-membered ring, and 3-membered rings are even less likely to form than the 5-membered rings we just showed in the previous one. Yeah, except we have direct evidence that this actually happens. That's why this mechanism is valid. For those of you being like, that sounds kind of hypocritical, it is. I wish I had something better to say for you, but that's just the way it is. Okay? So there are some reactions, intramolecular reactions, that will happen, but you really want to avoid them as much as you possibly can. Okay? Let's throw on another intramolecular or intermolecular here. If we go through and look at this as an intermolecular reaction, we're now attaching these two very long floppy chains. Remember, those floppy chains can freely rotate. So what we are effectively doing is taking two, and noodles even doesn't work all that well of an analogy because noodles are still, there we go, spaghetti. Okay, cooked noodles of spaghetti. Okay, and we are flopping those cooked noodles of spaghetti around so that two ends connect. Okay, what are the odds that that's going to happen cleanly? Yeah, that's going to be kind of hard to get that to happen. It can still happen, okay, but that's going to be a challenge. However, what happens if that flopping noodle of spaghetti, because even like as you start to wave that around, eventually it's going to start to coil up on itself a little bit. And if it coiled up on itself, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, isn't that carbon quite positive? Couldn't those electrons go right there and connect out? Yeah. Well, that's an intramolecular reaction. We shouldn't do an intramolecular reaction. Well, it's not that we can't do them, it's there has to be a good reason to do them. Why would there be a good reason to complete the intramolecular reaction here? What do we end with? We end with a 6-membered ring. 6-membered rings are quite stable. So your intramolecular reactions are allowed to happen, and the big when they're allowed to happen is when you form really stable structures like 6-membered rings. Okay, and so Cardy's got that kind of nicely shown here, and it's even his wording isn't all that nice. Okay, the intramolecular wins out over the competing intermolecular reaction. Okay, and that's assuming we form that 5 or 6-membered ring, because that now makes it a little bit more stable. Okay, so with that, we have the end of Unit 3. No more videos from me unless you specifically request individual topics, which means they'll probably be shorter videos. So with that, I hope you've spent some significant amount of time studying for the exam, and that this is not the night before the exam when you finish this video. Thank you for having listened to all of those